Something I introduced before when I was talking about variability is multiple sampling. So what happens when I collect more than one sample? So you have to understand that sampling is an estimation. It can be affected by bias, and understand that you have to calculate this thing called the standard error of the mean. Now, if I have multiple samples, a single one might be misleading. It's better to be able to collect more than one. Now, with opinion polls, this happens quite commonly. It's not so frequent in experimental conditions, purely because of the cost of collecting the data. If you collected it once, why do you want to collect another sample again? How can you justify the expense of the equipment needed to do it, the reagents if you're doing something such as a genetic test? Can you afford to do it? Opinion polls, much easier. So the example we use is the one out of the Obama against Romney election, and you can see that they change. One is different to another. So if I was going to do an estimate of the mean votes for one particular candidate, which of the samples should I use? Which of the polls should I include? So the difference in the numbers could be caused by bias, that I'm not picking a fair group of people. So if I go to certain places, I can ask, if I go to Mar-a-Lago and I go, oh, are you going to vote for Trump? Then they're going to say yes, because they're inside Trump's own home, his own building, his property that he owns. But if I go to other areas, they're not likely to be Trump voters, for example. So I can bias and skew things. One way that people do that is they can skew to remove people who are very seriously ill out of a clinical trial. Also, sampling could be inaccurate because there's lots and lots of variability. You don't intend it, but by accident you end up with a subgroup that aren't representative of the rest of the group. Or there can be something that's actually different in the populations or different in the experiment. Now, standard deviation describes the variability of a sample of data that you collect. Now, the standard error describes the variability between these different samples of data. So if I collect multiple samples and I plot the distribution of all these multiple samples, I will still end up with the normal distribution, and they will be spread around the center of that distribution will be the population mean, and the spread of it, the width of it, will depend on the standard error of the mean. Now, because we don't want to collect loads and loads of samples, we can use the standard deviation to estimate the standard error. Now, it's a biased estimate, which we discussed before, unless you divide by n-1. This is based on the law of large numbers, the other important statistical law, as well as the central limit theorem. So as the size of your sample gets bigger, the sample is getting closer to the size of the population, so the mean of your sample gets closer to the mean of the population. For very small samples, which unfortunately are the typical thing we're going to do in the lab because we're restricted in terms of finance and volunteers, then there's quite a lot of bias and it's a poor estimator. Now, the standard error of the mean is calculated by this. It's the standard deviation of your sample, S, divided by the square root of your sample size, the square root of n. Now, if you've got a very small sample size, so let's say less than 5 or 6, then this is going to be underestimated by about 25%. It should be much larger. As you get to reasonable size samples, so let's say 10 or 20 or 30, then this bias decreases. So the standard error of the mean should be written by that symbol SE with the X bar, because that's the mean. Why do you divide by root n? So you can work this out from the binomial distribution, which was done by a person called de Marve in 1730. So I've created some simulations in R which allow you to actually see this happening. In the first, the sample size is 10, the second is 1,000, and the second sample is 100 times larger, but the standard deviation is only 1/10. So this is showing practically what happens when you apply de Moivre's law, and that's why you divide by root n.